Okay, good morning everybody. Oh, you guys still can't see the thing. There we go. Okay, good morning. Today I'm going to learn some more math. No warm-up problems today, so we're going to jump right into the lecture. So we're going to start kind of building out some material in terms of what sorts of things can we use derivatives to do. Okay, so first we kind of described what is a derivative. Okay, that's when we were talking about instantaneous rates of change and that sort of thing. And then we talked a lot more about how to actually compute derivatives. So far we've talked about exactly one application of derivatives. Well, I guess two applications of derivatives. One's for marginal cost and marginal revenue, marginal profit. Those are the derivatives of the cost, revenue, and profit functions. And another application that we learned was the tangent line approximation. So if we know the derivative, we can find the equation of the tangent line and use that to approximate our function. Okay, so the first, what we're going to talk about today is kind of like the first and, well, maybe most well-known applications of derivatives. It's for finding minimums and maximums of functions. Okay, so we touched on this a little bit already, but we're going to make it a little bit more clear. So we'll talk about how to find the minimums of a couple of functions, and we'll talk about what it means for something to be a local minimum, local maximum, and we'll talk about critical points. So critical points are basically going to be potential spots where we might find a local min or a local max. Okay? All right, so the first thing to consider is just this graph here of this parabola. G of x equals x squared minus x minus 2. And we're supposed to estimate the value x at which this function achieves a local minimum. Okay, so if I were to look at this graph here, when I say that the graph achieves a minimum, the minimum that I'm referring to is the minimum height. Okay, minimum height. So the place where this graph achieves a minimum is right here. Maybe I'll make it a different color. Blue. Right here at the bottom, okay? That's when I reach a minimum. Okay, so if I were to be riding a roller coaster, it would be the point at which I hit the bottom, right? Okay, likewise a max is going to be when I hit the top. Okay, and so if we want to describe the value of x at which this function g attains a local minimum, well, we ought to take this point up to the x-axis, and remember that x is the variable which describes the position of a point in terms of how far to the left or how far to the right we are, okay? So it looks like g attains a maximum at x equals, or excuse me, a minimum at x equals 1/2. Okay, so that's just kind of a visual problem here. Okay, and so now we're supposed to look at the point associated with the local minimum of g. And let me ask you guys, what do we think is happening with the derivative of this function at this point here? I'm referring to the blue point at the very bottom. What value do we think the derivative is taking at that point? Yes?
Would it be 0?
It will be 0. Okay, and here's why. If I were to draw in the tangent line here, what would it look like? Well, remember a tangent line, we just take, one point on it and draw a straight line that just comes in and barely touches it one time. So if we do that at this point, the line is going to look completely horizontal. Okay? So g prime of x is equal to 0. Okay, so this is maybe indicating that when our derivative is 0, we might be hitting a max or a min. Okay, that's what's being indicated here. All right, so let's compute the derivative of g and actually check. Well, if I have g is equal to x squared minus x minus 2, then g prime should be equal to 2x minus 1. Okay, so that's pretty standard application of doing a derivative of a polynomial. And now we're supposed to use the property of the local, this should say minimum, that you stated in part B, and the formula that we computed in part C to exactly compute the value of x at which g attains a local, again, this should say minimum. Well, for now, our hypothesis, our working hypothesis is that we will achieve a minimum when the derivative is 0. So we computed what the derivative is. So in order to find the x value that causes the derivative to be equal to 0, I need to solve the equation 2x minus 1 equals 0. And if I ask for what x value does that happen, well, I just solve this algebraically and I get x equals 1/2. Hopefully that didn't confuse anybody. I added 1 to both sides and then I divided by 2. Okay, so this is kind of our first look at this minimum and maximum thing. And what we're about to see is that we haven't really completely described the picture here. Okay, but so far our working hypothesis is derivative equals to 0 is a good indicator that we might be reaching a minimum or a maximum. Okay, but now we're going to consider something a little bit more complicated, and we're going to see why our previous rule isn't exactly covering all possible cases. Okay, so here we have a function. It's the function absolute value of x plus 2. Okay, and we're supposed to kind of do the same process here. So if we want to estimate the value of x at which this function attains a local minimum, just look for the smallest height. It looks like it's happening right there, and that looks like it happens when x is equal to -2. Okay, and now herein lies the issue with our previous kind of hypothesis. How does the derivative f prime behave at this point? What do we think? Should the derivative be 0 at that point? If I were to draw a line which comes in and touches our graph of our function at exactly this point and no other points, what might it look like? Yeah, Kevin?
Could really look like anything.
Yeah. Could look like anything, Kevin says, and I think what he's getting at is, sure, this one works again. like before. But what about this one? Or this one? All of these lines have the property that they are a tangent line to the graph of f at the point -2, 0. Okay? So there's a really big issue here, which is I'm asking you to tell me what is the slope of the tangent line, and you come back at me and say, which one? Right? You guys see how this is a problem? You can't really say what the slope of the tangent line is because there are many tangent lines. So in this case, what we say is that f prime of x, well, I should say f prime of -2 does not exist. Okay, it does not exist. So I think it would be good if we could have taken a few more days to talk about really what it means for the derivative of a function to exist. But I'll give you guys the short version, which is basically if our graph is either discontinuous or our graph is sort of pointy like this, that's going to be when our derivative's not existing, okay? So if our function looks like a step function like this, for example, we say the derivative does not exist at this point x. So if we have jumps like that, or if we have a function which looks like this and it has a little hole here, so this is DNE situation, this is a DNE situation, and the last one is if our graph is pointy at all, then at either of these points x or y, why don't we call it x1 and x2, we're going to have derivative not existing. Okay, so how does the derivative f prime behave at this point? F prime of -2 does not exist. That's what DNE stands for, does not exist. Okay. So our original theory was kind of, we think that a function will achieve a local minimum when the derivative is equal to 0. How can we expand that hypothesis to include cases such as this one? So to be clear, I want to write a statement that says f will have a local min or max when ... Previously, I had written f prime equals 0. And we just put a period here and said done. But we found out with this case that that's not exactly an all-encompassing hypothesis. Can I modify this sentence to include situations such as this? Have I confused everyone, or is everyone a little bit hesitant to answer? Like, for example, I could erase this period here and put the word or. What should come now? Okay. What was different about this case with this absolute value function from the parabola function? What was different between those two things? Kevin?
Could you just say, or it doesn't exist?
Exactly. F prime equals 0 or F prime does not exist. Okay? Now these are the ways that I might locate a local maximum or a local minimum. Okay? One of these two things should be true if we have a local minimum or a local maximum. They do not necessarily imply that we have a local minimum or a local maximum. Okay? So what I really should say is not F will have a local min or max. I should say F may have a local minimum slash maximum when F prime equals to 0 or F prime does not exist. Okay? So this is the definition of a critical point. Okay? A critical point, which they call P comma F of P, is a point on the graph such that F prime of P equals 0 or F prime of P does not exist. That's what it means for something to be a critical point. So, in our case, our critical point for this problem was -2 comma 0. -2 comma 0. We said that it's a critical point because it satisfies one of the two criterion that define a potential critical point. A critical point either has derivative not existing or derivative equal to 0. Okay, one of those two things, either or. So -2 comma 0 is our critical point. And it turned out that for this example, our critical point was a local minimum. Okay? Now, let me quickly give you an example of a function which has a critical point but doesn't have a local minimum. It might look something like this. It might come down like that and then go off like that. Okay? So the reason that this is not a minimum is because if I'm riding my roller coaster on this thing and I hit this point right here, I haven't reached the bottom of the roller coaster yet. It's going to be a very bumpy ride. I'm going to suddenly start going in a different direction. But I'm going to keep going down. So if this is the point x comma, why don't we call it p comma f of p? This is p comma f of p. Then p comma f of p is a critical point. But not a minimum. Okay, so if we want to know about the minimum and maximum structures of a function, we need to investigate all of the critical points. And one by one, we'll decide on a case-by-case basis whether we think that critical point corresponds to a local max, a local min, or neither, such as in the case of this red function. Yes?
Do you mind going back to the definition?
Yeah, sure. Yes, so having either of the above properties, being f prime equal to 0 or f prime does not exist, we call that point a critical point of the function. And the critical value of f is the value f of p at the critical point p. Okay? I won't get too hung up on the critical value part. Really what we want to say is this point here is what we will describe as the critical point. Okay? Yes?
So even though a point may not be a local maximum minimum, it's still a critical point?
Exactly. Such as in the case of the red problem, p comma f of p here is a critical point, which means that it sort of is a candidate for a local max or a local min. However, upon closer investigation, it wasn't. Okay? So, what I know is that if a function has a local minimum or a local maximum, then it will occur at a critical point. This does not imply that a critical point is necessarily a local max or a local min. That's kind of the point that I'm making here. Okay, thank you for your questions. Any other questions about the critical point definition? All right, let's do some practice then. So we want to find all the critical points of this function f of x equals 3x to the power 5 minus 5x cubed. Okay, so we want to find these critical points. So, in particular, we're concerned with where f prime is equal to 0 or f prime doesn't exist. Okay, so the first thing we should do is compute f prime of x, and then we'll sort of talk about where it might be 0 or not exist. So using the power rule, this first term, 3x to the power 5, I just bring that power 5 down front and multiply. It becomes 15, and then the power on x should decrease by 1, so I'll get 15x to the 4th power. Okay, now I just need to do the derivative of the second part. That's 5x cubed. I multiply down the 3, I get 15 again. X to the power 3 minus 1 is 2. Okay, so if you had a graphing utility, you could graph this function here using Wolfram Alpha or your graphing calculator or whatever. And it's going to look sort of like a parabola, basically. We could factor this, for example. You take out a GCF, 15x squared times x squared minus 1, right? So if we were to graph this thing, what would it look like? I think it's going to look something like this, maybe. Some kind of quartic function. Okay, so we want to know where these properties are satisfied. So let's talk about just the first one, f prime equals to 0. Okay, we want to find the points where f prime is equal to 0. So what I'm going to do here is set this whole equation equal to 0. And now I want to entertain what values of x might cause this equation to be true. Can someone give me one of the values of x that will cause this to be true? Kevin?
0.
Yeah, 0 is one of them. That's because we've got this x squared out front. So this implies x equals 0, or The other possibility is if this inside function is equal to 0. Well, x squared minus 1 will be equal to 0 when x takes the values blank and blank. Help me out. Yeah.
1 and -1?
Yeah, 1 and -1. If we take 1 squared, subtract 1, we get 0. If we take -1 squared, we again get 1, subtract 1 is 0. So, or x equals 1, or x equals -1. Okay. So thankfully, the problem told us that we should get 3 values of x. So since I've already gotten 3, I'm not really going to worry too much about the DNE situation. And I'll briefly describe why we don't need to worry about the DNE situation. All polynomials have the existence of their derivative everywhere. Okay, well, let me write that down. Well, actually, yeah, okay, I'll write that down. All polynomials have an existing derivative for all values of x. Okay? So, if you remember, I spent some time and placed some emphasis on identifying polynomials. Okay? Remember, we said that a function is a polynomial if it can be expressed as a sum of non-negative integer powers of x. Okay, so for example, things like x cubed plus 17 are a polynomial. Things like x to the 1/2, not a polynomial. Okay? 6x to the 15 minus 4x cubed minus pi x minus e. Polynomial or not polynomial? So hands up for polynomial. Not polynomial? Anybody? Okay. It is a polynomial, and the only thing we have to do is look at the powers. 15 is a non-negative integer. 3 is a non-negative integer. 1 is a non-negative integer. And 0 is a non-negative integer. Okay? So this is a polynomial. So the amazing fact here is that all polynomials have an existing derivative for all values of x. So in particular, if we want to find the critical points of a polynomial, we don't have to entertain the second possibility that f prime might not exist. Okay, so let's actually express the critical points here. So x equals 0. If we plug that into our original function, f of x, what are we going to get? We're going to get 0 back, right? So 0, 0 is a point on the graph of f of x where the derivative is equal to 0. We also have x equals 1. If we plug 1 into our function f, we're going to get 3 minus 5, which is going to be -2. And the last one, x equals -1. If we plug that into our original function, we'll get -3 minus -5, Yeah, -3 minus -5, so we get 2. Okay, great. So these are our critical points. Okay. Are there any questions about how we found the critical points? Okay, we were fortunate to have a function which is nice and smooth, so we didn't have to worry about the derivative not existing component of critical point finding. Okay? If you're a little bit hazy on solving polynomials for zeros, such as this process that I did here to find out that, x is 0, x equals 1, and x equals -1 are going to cause this equation to be 0, come see me in office hours. I have office hours later today. Okay, how am I doing on time? Plenty of time. Okay, so here's the actual graph of this function. Okay, so let's draw on our critical points. We know there should be a critical point at the point 0, 0. So that's right here at the origin. Oh, come on. Right here at the origin. We know there should be a critical point at -1, 2. That's this point way up here. Oh, come on. This point way up here. And then we know there should be a critical point at 1, -2. So that's way down here. Okay? So, the critical points we have found are points on the graph where the tangent line has slope 0. If I draw the tangent lines at all these points, they will have slope 0. Okay? As we can see, this function is nice and curvy and smooth. We don't have any jagged edges. And that is exactly because this function is a polynomial. Polynomials wiggle around in nice, smooth ways with no pointy edges. Okay. So now, let's classify the critical points, x equals -1, x equals 1, and x equals 0, as local maximums, local minimums, or neither. Okay, so we can tell here that this point here, corresponding to x equals -1, it's a peak, right? If I was riding my roller coaster, that would be the highest part. Okay? We call that a local maximum. Okay? So, x equals -1 corresponds to a local max. And now this document we have is going to ask us a couple of leading questions that are going to help us figure out, if we know that there's a critical point, how do we determine whether or not that critical point is a local maximum or a local minimum or neither without looking at the graph? Okay? And the key thing to check is, how does the derivative f prime behave to the left of x equals -1 and to the right? Okay, so getting a little bit abstract here. The derivative, remember, is the slope of our function. The slope to the left of our function has what sign? Should it be larger than 0 or less than 0? So I'm talking about the slope of our function at, say, this red point here. Do we think positive or negative? It's positive, right? If we were to draw the tangent line, it might look like that. Positive slope. Now to the right of our point, the slope is going to be negative. Okay? So what is this all to say? This is all to say, if I'm riding on my roller coaster and I'm going up, and then some very short time later, I'm going down, what can you surmise happened in between these two pictures? Yeah, Kevin?
You hit the maximum.
Yeah, we got to the top of the roller coaster. Okay? That's what's going on here. So, this is all to say, if I'm going up and then going down, I hit a maximum. Okay, so let's actually answer the question. To the left of x equals -1, we have f prime greater than 0, and to the right we have f prime less than 0. Okay. Now let's talk about the critical point at x equals 1. So switching gears to talk about this critical point corresponding to the x value x equals to 1. Looks like a local minimum to me, because we're going to be bottoming out. Now let's try to apply the same kind of logic in terms of what's happening with the derivative of f. Well, before I hit the bottom, my derivative is looking quite negative. And after that, my derivative is looking quite positive. Which is to say that if I was riding a roller coaster and I was going down, and then some very short time later, I was going up, then you can surmise that I bottomed out. Okay? That's what's going on here. So, let's make it mathematically rigorous. X equals 1 corresponds to a local minimum, and the behavior is to the left, f prime is less than 0, and to the right, f prime greater than 0. Okay? All right, let's talk about the problem child. The problem child is this critical point here in the center. Okay. What do we think? Local max? Local min? Or neither? Yeah? It's going to be neither. Right? If I'm riding my roller coaster, I'm going down, 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 and then I kind of bottom out a little bit, but then I start going down some more. Okay, that's what's happening here. So this is kind of like that example of the like absolute value looking jagged thing that we did, where we started going down and we had a discontinuity or a critical point, and then we were still going down after that, so it wasn't a minimum. So let's talk about it in terms of the behavior of the derivative. Here our derivative was negative, and then immediately after, our derivative was again negative. So how can we put that mathematically? F prime does not change sign. So x equals 0 does not correspond to a local max or a local min. So neither is the answer. Okay. So now we have everything we need to kind of classify when we're going to have a local min, local max, or not at all. The first step is it should always happen at a critical point. Once we have a critical point, we can classify each critical point into either a local max, a local min, or one of these problem children, which is just neither. Okay, that's how this critical point game works. So, based on our observations in problem 5, let's come up with a method for classifying critical points of a function f as local maxima, local minima, or neither. So, if f prime goes from being positive to being negative, then f has a blank. Who can fill in that blank for me? If our derivative goes from being positive to being negative, should it be a local max or a local min, or neither? Ashlyn? So if we're going from being positive, we're going up, and then later on we have a negative slope going down. Maximum, yeah. So we should have maximum here. Okay, it's always useful to draw these little arrows, okay? And remember, we're moving from left to right here. Okay, so when I say f prime goes from being positive to being negative, what I mean is to the left, the derivative's positive, and to the right, the derivative's negative. I recommend drawing these arrows like this to help you kind of remember. Okay, and now the next one. If f prime goes from being negative to being positive, then f has a local minimum. Okay, the way I would draw the arrows for this is negative slope first, then positive slope. If I was riding my roller coaster, that would mean that I hit the bottom. Okay, and the last thing, we don't even really need to categorize it. We can just say if neither of the above things happen, then it is not a max or a min. Okay, so we have kind of two things that can happen. The third choice is for neither of those things to happen, in which case our critical point is neither a local max nor a local min. Okay, I got 4 minutes. Let's see here. Do I have time to... Oh man, I was supposed to get through that today as well. Okay, we'll do this last part, and we'll save the rest for another day. So we'll consider this function here, x cubed minus 9x squared minus 48x plus 52, and we're supposed to find the critical points of f. Again, we're given a polynomial. So I'm not going to need to concern myself with the derivative not existing anywhere on this function. So the only thing that I need to find out is when is the derivative 0. That will tell me when I have critical points. So first I should find the derivative. It's going to be 3x squared minus 18x. Okay. Minus 48. And we want to know when is this equal to 0. Well, we could use the quadratic formula. I think we can be a little bit more clever than that. I think we can divide both sides of this equation by 3. We'll have x squared minus 6x minus 16 is equal to 0. And I could solve this using the quadratic formula, or I can factor. Does anybody know how this factors? Yeah? Very good. X minus 8 and x plus 2. If we FOIL this out, we'll get x squared minus 6x minus 16. Okay, so this implies that one of those two things is equal to 0, which means that x is equal to either 8 or x is equal to 2. Negative 2, excuse me. Okay, so these are going to be the points where we have a critical point. And if we want to classify them as minimums or maximums, what we're going to do is the following. I'm going to put a little number line here. On my number line, I'm going to put my 2 points. Here's negative 2. And here is positive 8. And I want to know, how does f prime behave in each sub-interval? So, what I'm going to do is choose a point from each of these 3, oh, jeez, that was awful. Each of these 3 intervals here. And I'm going to evaluate f prime at these points to determine whether we have a situation that looks like, I don't know, plus and then negative and then plus, or maybe negative and then plus and then negative, or something like this. Okay, this is the strategy that I'm going to do. But I don't think I have time to give it my full attention, so we'll stop here today and I'll finish this example next time.
Just wanted to let you know.
Okay.
I'm going up to North Carolina to visit family, so I'm going to watch the lecture on Wednesday, but I'll be here Friday.
Okay, no problem. Yeah, no problem.